Welcome to Module 1 of our course on Introduction to Computer Engineering. In this module, we'll start with the very building blocks of digital electronics, logic gates, Boolean algebra, and number systems, and build our way toward designing working combinational logic circuits. By the end of this module, you should be able to understand the behavior of basic logic gates, apply Boolean algebra to simplify logic expressions, use Carnot maps for logic minimization, convert numbers between different bases, represent and manipulate sign numbers, design combinational circuits like adders and subtractors. Section 1. Basic logic gates. The foundation of computer engineering rests on logic gates. These are tiny electronic switches that process binary inputs and produce binary outputs, based on specific rules. The three primary logic gates are AND gate, outputs 1 only if all inputs are 1. OR gate, outputs 1 if at least one input is 1. NOT gate, inverts the input, 1 becomes 0, and 0 becomes 1. From this, we derive three other useful gates. NAND gate, not of AND. NOR gate, not of OR. XOR gate, exclusive OR, outputs 1 if the number of ones at inputs is odd. And finally, the XNOR gate, the exclusive NOR, which is the inverse of XOR. Truth tables. A truth table lists all possible input combinations for a gate and shows the corresponding output. This is the most reliable way to describe gate behavior for design purposes. Section 2. Boolean algebra. Boolean algebra is the mathematics of logic. It uses binary values, 0 and 1, along with operations like AND, OR, and NOT. Basic laws of Boolean algebra. Identity law, combining with 0 or 1 leaves a value unchanged. NOR law, combining with 0 or 1 produces fixed results. Idempotent law, combining a variable with itself doesn't change it. Complement law, a variable ANDed with its complement is 0, ORed with its complement is 1. Distributive law, similar to regular algebra but works with logic operators. De Morgan's theorems, convert AND to OR with negations and vice versa. Section 3. Logic minimization. We rarely use a logic expression in its raw form, instead, we simplify it. Simplification means fewer gates, lower cost, less power consumption, and higher efficiency. Minimization methods. Algebraic simplification. Applying Boolean rules to reduce expressions step by step. Carnot maps, K-maps. A graphical method for spotting patterns that allow grouping of terms to simplify expressions. Works well for up to 4 to 6 variables. Section 4. SOP and POS forms. Sum of products, SOP, ORing together multiple and terms. Product of sums, POS, ANDing together multiple or terms. NAND only and NOR only implementations. We often implement circuits using only NAND gates or only NOR gates because they are easy to manufacture. They can replicate any logic function. This requires converting SOP forms to NAND only and POS forms to NOR only equivalents. Section 5. Number systems. Computers use binary internally, but humans use decimal. We also encounter octal and hexadecimal in computing. Common bases. Decimal, base 10, digits 0 to 9. Binary, base 2, digits 0 and 1. Octal, base 8, digits 0 to 7. Hexadecimal, base 16, digits 0 to 9 and a F. Number conversion. We must be able to convert from decimal to binary, octal, or hex. Convert between binary, octal, and hex directly. Convert from binary back to decimal. Section 6. Representing negative numbers. Digital systems must handle both positive and negative numbers. 3 common methods. Sign magnitude, the highest bit indicates sign, the rest is magnitude. 1's complement, negative numbers are formed by inverting all bits of the positive number. 2's complement, invert all bits and add 1. This is the most widely used because it simplifies arithmetic. Section 7. Arithmetic circuits. Once numbers are represented in binary, we can create circuits to add or subtract them. Half adder and full adder. Half adder adds 2 single bits. Full adder adds 2 bits plus a carry-in. Multi-bit adder/subtractor. By combining multiple full adders, we can create a multi-bit adder/subtractor for 2's complement numbers. Overflow detection is important. It occurs when the result exceeds the range representable by the number of bits. Section 8. Combinational logic devices. Decoders. Convert binary inputs into a one-hot output, where only one output line is active. Encoders. The reverse of decoders, convert multiple inputs into a binary code. Multiplexers, MUX. Select one of many inputs to pass to the output. We've covered a lot of ground. Logic gates and Boolean algebra. Minimization techniques. Number systems and signed number representation. Combinational devices. With these foundations, you're ready to move on to Module 2, where we'll shift from combinational logic to sequential logic, microcontrollers, assembly language, and memory systems.